I want you to imagine that you are standing in a dark room with no windows. In your hand is an old brass pocket watch. You can feel its weight in your palm. You can hear the ticking. Each click gives you a before and an after. One moment becomes the next, then the next. And without thinking about it, you've accepted the most ordinary assumption in human experience: time has always been there, quietly arranging reality into a sequence. Now imagine turning the watch over and discovering that the first number on its face is not 1, it is 0. And behind 0, there is nothing: no hidden gear, no earlier tick, no empty space waiting in darkness. The mechanism itself simply begins. That is roughly where modern cosmology leaves us when we ask one of the oldest questions a human being can ask: what came before the Big Bang? For decades, the safest answer was that the question might not even make sense. If time itself emerged with the early universe, then asking what happened before the Big Bang could be like asking what lies. North of the North Pole, the grammar survives, the geometry does not, and yet something remarkable has happened. Our equations have become more ambitious. Our telescopes have reached deeper. Our gravitational wave detectors have become sensitive to motion so small that they can measure distortions in space-time, far smaller than the width of a proton. And theorists have learned that the Big Bang does not necessarily have to be the absolute beginning. It may have been a transition, a boundary, perhaps even a bounce. I need to be precise here. Scientists have not photographed another universe before ours. No telescope has looked through the Big Bang and taken a picture of yesterday. There is no confirmed measurement proving that a prior cosmos existed. But several serious physical models now describe ways in which something could have preceded the hot, expanding universe we observe. Some of those models make predictions, and predictions can be tested. That changes the question. Instead of asking what came before the Big Bang as philosophy, we can begin asking whether our universe contains fossils from an earlier state. That is the door, and what may be written on the other side of it is stranger than any creation story our species has ever told. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. Do you want to follow the places where established physics ends and the unknown begins? You are in the exact right place. Now, I want you to forget the image of the Big Bang that almost all of us were given as children. It was not a bomb exploding into empty space. There was no central point from which matter flew outward into a pre existing void. On the largest scales, space itself expanded. Every region separated from every sufficiently distant region because the geometry of the universe changed. Hold onto the pocket watch. The watch represents space time itself. The ticking is time. The brass case is space. The gears are matter and energy. And Einstein taught us something profound. You do not really get to pull those pieces apart. Matter tells space-time how to curve, and curved space-time tells matter how to move. If we run the equations of general relativity backward, the universe becomes hotter, denser, and more compact. Galaxies approach one another. Atoms cannot survive. Nuclei dissolve into a plasma of particles. Eventually, our familiar equations are pushed toward conditions of extraordinary density and curvature. If we continue recklessly, classical general relativity leads toward a singularity. And that word has caused enormous confusion. A singularity is often described as a physical point of infinite density, but many physicists interpret it more cautiously. Infinity in an equation is frequently not a discovery, it is a warning label. It tells us that the theory we are using has been pushed beyond the region where it can be trusted. Imagine using a street map to navigate the inside of an atom. The map does not become wrong because the atom is mysterious. It becomes useless because it was never designed for that scale. General relativity is extraordinarily successful at describing gravity, planets, stars, black holes, gravitational waves, and the evolution of the cosmos. Quantum mechanics is extraordinarily successful at describing atoms and elementary particles at the earliest conceivable moments of the universe. We need both at once. And we still do not possess a fully tested theory of quantum gravity. That missing theory sits precisely where the word beginning is usually written. For much of the 20th century, this left cosmologists with a magnificent but incomplete picture. The universe expanded from a hotter, denser state. The cosmic microwave background gave us a photograph of the cosmos when it was only about 380,000 years old. The abundance of light elements matched calculations from an even earlier era. The expansion of space could be measured in the motion of galaxies. The Big Bang framework succeeded spectacularly, but then another problem appeared. The early universe was almost absurdly uniform. Look at opposite regions of the cosmic microwave background, and they have nearly the same temperature, even though in the simplest Big Bang picture, those regions should not have had enough time to exchange information. The geometry of the universe also appears remarkably close to flat, and hypothetical relics predicted by some high energy theories were nowhere to be found. In the early 1980s, cosmic inflation offered an elegant solution. Inflation proposes that an extremely early patch of the universe underwent a brief period of extraordinary accelerated expansion. A region small enough to have been causally connected could have been stretched to cosmic size. Tiny quantum fluctuations could have been magnified into the seeds from which galaxies eventually grew. In this picture, the hot Big Bang is not necessarily the absolute first event. It is what happens when inflation ends and the energy associated with that inflationary phase is converted into the hot mixture of particles and radiation from which our familiar cosmic history develops. This is an important distinction. When people say the Big Bang, they often mean the beginning of everything. In modern cosmology, the phrase is often used more carefully for the hot, dense, expanding phase after inflation. And suddenly the pocket watch has acquired a hidden compartment. The phase still begins at zero, but perhaps the mechanism was already moving beneath it. Here is the hard truth. We do not know what powered inflation. We do not know whether inflation was the first physical state. We do not know whether it lasted for a finite interval or emerged from something even deeper. And some theorems suggest that inflationary spacetimes, under broad conditions, cannot simply be extended forever into the past. So inflation may push the beginning backward without eliminating the mystery. This is where the universe, as I have learned time and time again, reveals its deeply humbling sense of humor. Every time we move the boundary asks another question. To understand the alternatives, I want you to imagine a second object, a rubber ball. You drop it onto a hard floor. It falls, compresses, stops for an instant, and rebounds. Now replace height with the size of the universe. A conventional, singular Big Bang story runs the film backward until the universe becomes smaller and smaller and smaller, eventually reaching a point where our equations fail. A bouncing cosmology asks whether that failure is artificial. What if the universe did not begin by emerging from a singular point? What if it was contracting before it expanded? In that picture, the Big Bang becomes a big bounce. A previous cosmic phase contracts, density and curvature increase, but before an actual singularity is reached, new physics intervenes, the collapse reverses, expansion begins. The ball strikes the floor and rises again. Hold on to that image. There are several families of bounce models, and they do not all work the same way. Some emerge from attempts to quantize spacetime. In loop quantum cosmology, for example, the smooth continuum of classical spacetime is replaced at extreme scales by a quantum geometry. Under certain mathematical treatments, the gravitational behavior near what would classically be a singularity can change. Instead of infinite compression, a maximum density is reached and the universe transitions from contraction to expansion. This is not established fact. It is a theoretical result inside a particular approach to quantum gravity, but notice what has happened. The word before has become mathematically legal. Again, there can be a prior contracting branch. There can be physical evolution on the other side. There can, in principle, be traces. And traces are where speculation becomes science. Suppose you walk into a quiet room and see a glass of water trembling on a table. You did not hear a sound. You did not see anything happen, but the ripples tell you that something disturbed the room before you arrived. Cosmologists search for exactly that kind of ripple, not in water, in space-time. Gravitational waves are distortions in space-time that propagate through the universe. Violent astrophysical events such as merging black holes can produce them. But the early universe may also have generated backgrounds of gravitational radiation. Different theories predict different spectra, different strengths, different statistical fingerprints. A pre Big Bang or bouncing phase could, under some models, leave a stochastic gravitational wave background with a characteristic frequency dependence. That means detectors such as LIGO and Virgo can do something extraordinary. They can test aspects of a universe they cannot directly see, and the current result is not a discovery, it is a constraint. Searches using gravitational wave data have looked for signals predicted by certain pre Big Bang models and found no evidence for such a background. That does not prove there was no prior phase. It means portions of parameter space can be restricted, and future detectors may test much more. This distinction matters. Science often advances not by hearing the expected knock on the door, but by discovering how quiet the hallway really is. The absence of a signal has structure. It tells us which models must change, which survive, and where the next experiment should listen. Now I want you to look around the room you are sitting in. Every object you see exists because tiny fluctuations in the early universe were amplified over billions of years. Regions that were slightly denser accumulated more matter. Gravity deepened those differences. Stars formed, galaxies assembled, heavy elements were forged, planets condensed. You are, in a literal sense, downstream from ancient irregularities. So, if a universe existed before ours, the most profound question is not simply whether it existed, it is whether it touched us. Could patterns from a prior phase have crossed the bounds? Could they have influenced the density fluctuations that became galaxies? Could they have left unusual signatures in the cosmic microwave background? Could primordial gravitational waves retain a memory older than the hot Big Bang? And this is where the problem becomes extraordinarily difficult. A bounce cannot merely exist mathematically, it has to produce a universe like ours. The fluctuations have to behave correctly. The resulting spectrum must match observations. Instabilities must be controlled. The transition has to avoid pathological behavior. And whatever new physics creates, the bounce must eventually connect back to the well tested physics we already know. A beautiful idea is not enough. The universe does not grade theories on elegance, it grades them on survival. There is another approach that makes the story even stranger. I want you to imagine an endless sequence of tides. The ocean rises, the ocean falls, the shoreline disappears and returns. But now imagine that each tide is not water moving across sand. Each tide is a universe. Cyclic cosmologies propose that cosmic history may not be a single beginning followed by one expansion. Instead, the universe could pass through repeated phases. One class of ideas, often associated with ekpyrotic or cyclic scenarios, imagines a phase of slow contraction preceding the hot Big Bang. In some formulations inspired by higher dimensional theories, interactions between brain like objects can generate the conditions that lead to a new expanding phase. Again, this is not something we have observed directly, it is a model, but it is a model built to answer real physical questions, including how the early universe became smooth and how primordial fluctuations could have arisen without conventional inflation. The conceptual reversal is enormous. Inflation says the early universe became smooth because a tiny region was stretched violently. Ekpyrotic models say a period of slow contraction can suppress certain irregularities and prepare the universe for a transition. Two different roads can attempt to reach the same observed sky, and now cosmology becomes forensic. Which road leaves the right tire tracks? Primordial gravitational waves could be decisive because some inflationary models predict a particular pattern of tensor fluctuations, while many ekpyrotic models predict a very different signal. Cosmic microwave background polarization is therefore not merely a technical measurement. It is an interrogation. The sky is being asked how it was made. Future instruments may answer, or they may eliminate entire families of answers. There is yet another proposal so conceptually unusual that even explaining it requires temporarily abandoning our normal intuition about time. Imagine a sheet of paper with a circle drawn on it. Now enlarge the circle until its edge moves infinitely far away. In ordinary geometry, infinity feels like an ending. But through certain mathematical transformations, infinity can be mapped to a finite boundary. Conformal cyclic cosmology, associated with Roger Penrose, explores a remarkable possibility. The infinitely expanded future of one cosmic eon might be mathematically connected to the Big Bang of another. The intuition is roughly this: in an unimaginably distant future, if the universe becomes dominated by radiation and mass effectively ceases to set meaningful scales, the distinction between enormous and tiny can change under conformal geometry. The remote future of one eon could then be related to the beginning of the next. No crushing contraction is required in the same sense as a conventional bounce. The end becomes the beginning to a transformation of scale. It is one of the most audacious attempts to turn the question before the Big Bang into a physical framework. Claims have been made about possible signatures of previous eons in the cosmic microwave background, but those claims remain disputed and have not become accepted evidence for the model. And that sentence is worth holding on to. Disputed evidence is not no evidence, but it is also not discovery. This is the narrow ridge that serious cosmology has to walk. On one side is excessive caution, where we pretend untested questions are meaningless forever. On the other is sensationalism, where every anomaly becomes proof of a new universe. The honest path is harder. We ask what the model predicts. We measure, we compare, we fail, we improve. And sometimes, if nature is generous, a signal refuses to go away. There is an even deeper difficulty hidden beneath all of these models. The word before itself may be misleading. Return to the pocket, watch. What if time is not a fundamental component of reality? What if the ticking appears only when the gears organize themselves in a particular way? Some approaches to quantum gravity suggest that space-time may be emergent. Just as temperature emerges from the collective motion of enormous numbers of molecules, time and space might emerge from deeper quantum relationships. If that is true, asking what came before spacetime could be like asking what temperature a single isolated mathematical point has. The language may be trying to describe something that does not yet possess the property the question assumes. This is where human intuition entirely breaks down. You and I evolved in a world of middle-sized objects moving at slow speeds under weak gravity. Our nervous systems are spectacularly adapted to thrown stones, approaching predators, changing weather, faces, voices, food, and social relationships. We did not evolve to visualize a quantum geometry without classical time. We did not evolve to understand a universe whose beginning may be a boundary condition rather than an event. We did not evolve to imagine causality without a clock. And yet mathematics allows us to walk into these places. There are proposals in quantum cosmology in which the universe can be described by a wave function rather than a classical history. There are no boundary ideas in which the earliest state does not possess a sharp temporal edge in the ordinary sense. There are tunneling proposals. There are emergent universe models. There are scenarios involving eternal inflation in which our observable universe is one bubble among many. These theories do not all agree, and some cannot all be true. Perhaps none is complete, but their existence tells us something profound about the state of modern physics. The Big Bang singularity is not a comfortable final answer. It is a frontier. Here is the hard truth. We have extremely strong evidence that the observable universe was once hotter and denser. We have powerful evidence supporting many predictions associated with inflationary cosmology. especially the statistical structure of primordial fluctuations. But we do not yet know the fundamental mechanism of inflation. We do not know whether inflation was preceded by another physical phase. We do not know whether a bounce occurred. We do not know whether time itself remains meaningful arbitrarily far into the past, and we do not possess direct observational evidence of a universe before ours. So, why are scientists still taking the question seriously? Because the question is becoming testable. That is the shift, not a confirmed answer. A change in status. A century ago, gravitational waves were a subtle implication of Einstein's equations. For decades, they seemed nearly impossible to detect. Then, in 2015, instruments measured the space-time disturbance produced by merging black holes. Today, observatories are probing gravitational wave backgrounds across wildly different frequency ranges. Ground-based interferometers listen at relatively high frequencies. Pulsar timing arrays probe much lower frequencies by using rapidly spinning neutron stars as a galactic network of clocks. Future space-based detectors will open another band entirely. Cosmic microwave background experiments seek polarization patterns linked to primordial gravitational waves. Each frequency range is another archaeological layer. If the early universe produced a gravitational wave background, it may contain information inaccessible to ordinary light. Photons from the first hundreds of thousands of years were trapped in a hot plasma. Gravitational waves interact much more weakly with matter and could carry information from far earlier epochs. Potentially, they are messages written when the universe was too young to be transparent. And if a pre Big Bang phase generated them, the message could be older than the hot Big Bang itself. Think about the sheer weight of that. Human beings began by reading scratches on clay and then ink on paper, then electromagnetic signals from stars. Now we are building instruments designed to read the geometry of space time as a historical document. The universe may have an archive. Gravity may be the oldest handwriting in it. But recently, another layer of tension has entered cosmology from entirely different directions. Measurements of the present expansion rate do not perfectly agree depending on how the rate is inferred. This is the Hubble tension. Observations of the early universe under the standard cosmological model produce one value, while several measurements, based on relatively nearby astronomical distance indicators, produce a higher one. No consensus has established that this discrepancy requires a pre Big Bang universe. It may involve unrecognized systematics. It may involve new physics at later times. It may eventually shrink. But tensions like this remind physicists that the standard model of cosmology, powerful as it is, may not be the final layer. Similarly, increasingly precise surveys are testing whether dark energy is truly constant. If cosmic acceleration evolves with time, that would alter our understanding of the universe's history and future. And again, none of this proves a bounce, none proves a previous eon, none tells us what happened before inflation. And the importance lies elsewhere. Cosmology has entered a precision era in which apparently small deviations can become clues about foundational physics. The cracks are being measured, and that brings us back to the rubber ball. Suppose the ball really did bounce. What was the universe before impact? Perhaps it was an enormous contracting cosmos. Perhaps quantum geometry prevented singular collapse. Perhaps the previous phase contained stars and galaxies of a kind we would recognize. Or perhaps contraction erased almost everything, leaving only a small statistical memory. Perhaps there were many cycles. Perhaps what came before was not a universe in any classical sense. Perhaps time emerged from a quantum state for which before and after are approximate descriptions. Or perhaps the traditional intuition is correct and there simply is no physical before. These possibilities are radically different, and that is exactly why future data matters so much. A primordial gravitational wave detection with the right spectrum could transform the debate. A stringent non-detection could kill models that currently remain viable. More precise, cosmic microwave background polarization could narrow inflationary possibilities. Better measurements of curvature could test whether our observable universe carries hints of global geometry. New particle physics could reveal ingredients required by early universe models. Quantum gravity theory may eventually connect mathematical consistency with observational prediction. This is the moment everything changes because the question is no longer only what do we believe happened, and the question is what would each possibility leave behind? That is science. A theory must risk being wrong. A universe before ours is scientifically interesting only if some part of it can, at least in principle, reach into ours and become measurable. And the coin must land differently, the water must ripple, the gravitational background must have a shape, the cosmic microwave background must carry a pattern. Otherwise, we are telling stories, beautiful stories, perhaps, but stories. Now I want you to place your hand on the table in front of you. The atoms in your hand were formed from material processed by stars. Those stars formed because gravity amplified primordial fluctuations. Those fluctuations may have begun as quantum variations in an early phase of cosmic history. Trace the chain backward, and your own body becomes connected to the question. If inflation produced those fluctuations, then your existence carries the consequences of inflation. If a prior contracting phase seeded them, then in a very real sense, you may carry information whose ancestry passes through the Big Bang, not memory in the human sense, not recognizable fragments from another world. Statistical inheritance, a pattern passed forward through the deepest transition in cosmic history. This is why the question becomes almost existential. We tend to imagine ourselves as beings living late in the universe, but perhaps we are also products of events that occurred before the chapter we call the beginning. A ripple survives, a fluctuation grows, a galaxy condenses, a star ignites, carbon forms, a planet cools, a nervous system learns to ask where everything came from, and eventually the ripple asks about its own origin. There is a humility in that which I find difficult to express. Newton showed us that the same gravity pulling an apple downward governs the moon. Einstein showed us that gravity is geometry. Quantum theory showed us that certainty gives way to probability at fundamental scales. Modern cosmology showed us that the universe evolves. Inflation suggested that the hot Big Bang may not be the first page. Quantum gravity now asks whether the book itself is written on something deeper than space-time. Every revolution has expanded what the word reality is allowed to mean, and now it may be our turn. The next major breakthrough may not arrive as a photograph. It may be a spectrum, a polarization pattern, a subtle statistical deviation, a gravitational wave background so faint that extracting it requires years of observation. The signal may look insignificant to almost everyone, and yet encoded inside it could be an answer to a question older than civilization. Did our universe have a past before its apparent beginning? Journeys like this, deep into the bleeding edge of human knowledge, require time, concentration, and a relentless distinction between what the data says and what we wish it said. If you value that kind of exploration, below this video, you will see a button labeled Super Thanks. Supporting the channel there helps make these long form lectures possible. But whether you support the channel or simply continue thinking about the question, I want to leave you with the image we began with, the pocket watch. At first, we turned it over and found nothing behind zero. And then inflation gave us a hidden compartment. So the rubber ball gave us the possibility of a bounce. The tides gave us cycles. The trembling water taught us to search for traces. And gravitational waves gave us a way, perhaps, to listen. We have not discovered what came before the Big Bang. Not yet, but we have discovered that the boundary between science and that question is no longer where it once was. And the door is not open, but for the first time, we may be learning where the handle is. And if one day we turn it and find that our beginning was not a beginning at all, then the strangest question will no longer be what came before us. It will be this: